Good afternoon, everyone. I'm Michele Merelli, and I want to thank you for joining this webinar about the application of Particleworks in gearbox and e-motor cooling systems. We will see today why Particleworks is the most complete particle simulation able to provide not only cooling and lubrication analysis, but also solid temperature prediction, Python automation, air inclusion, and also granular or powder material. So the agenda of this afternoon is as follows. We will have a little bit of motivations and trends and why we need digital models. We will also provide some experimental validations that were carried out during the last years. And then we will go in detail about all the possibilities of simulation that Particleworks allows in this kind of systems, as I mentioned. At the end, I will also reference to the papers available, public papers, and also our next conference in June, that is the Particleworks experience. I will give you details about that because we will have many more, let's say, contributions and interesting results. So what are the motivations? We all know that the world we live in changed quite a bit in the last few years because of COVID, because of wars, because of supply chain shocks. This really pushed, all of this pushed for digitalization, okay? Especially in R&D and testing. We know from a McKinsey report that implementing simulation early on in the design phase, in the engineering phase, can speed up the time to market and also reduce development cost because we can have tests or R&D digitally everywhere without the, let's say, price increases. Actually, we can take advantage of decreasing hardware costs, GPU cards. We will see how that can impact the simulation times. Moreover, the cooling and lubrication aspects in bearings or gearboxes, it's an important aspect because as we can see here, there is a Rabinowitz law that suggests that approximately 5–6% of the GDP in US is lost, for instance, for lubrication that is not sufficient to prevent failure in the equipment. So really, still 70% of equipment failures in 2014 was due to lubrication problems. So it's an important topic. Let's see how Particleworks can allow for a fast R&D, let's say, workflow. So the basic idea is presented here. Instead of using a clear casing type of setup in the testing or in the development of a gearbox, we can have a digital model integrating the fluid distribution, the splash, and the churning losses connected with the oil phase. Okay, so this was one of the first customer in Italy, Comer Industries, and in 2016 they asked us, can you perform this kind of simulation from CAD to finish in less than 3 days? Back at the days, we couldn't, with traditional computational fluid dynamics, we couldn't have this kind of simulation times. Traditional mesh-based CFD took weeks for preparing the geometry and also for computing the solution. Particleworks, with the moving particle simulation approach, really speeds up both the pre-processing and the CPU or GPU time. Why is that? Why can we achieve such low simulation times? Well, because in this kind of system, we have a lot of splashing, a lot of free surface flow. And the methodology on which Particleworks is based, that is the moving particle simulation, allows for a dynamic mesh instead of a static, pre-calculated Eulerian grid. This means that the fluid is automatically initialized at the beginning of the simulation, and the dynamic mesh that results in the particle discretization is moving with the simulation and adapts and localizes the computational nodes where needed. Okay, we solve for the Navier-Stokes equation. We solve for the traditional equations that are found in conventional fluid dynamics, but in a much more efficient way. So the fact that we don't have to generate the mesh, the fluid mesh, allows us to use the CAD as it is. So we don't have to also clean the CAD, and the designer can change quickly the CAD and monitor the influence on the lubrication aspects. The numerical settings are very easy to set up, so the more engineers, not only kayak experts, can take on digitalization projects and can access CFD solutions. The fact that we can run on graphic cards, like NVIDIA graphic cards, makes the, let's say, hardware infrastructure, much easier to implement. So we don't have to create a cluster, but we can run on single workstations, decreasing the, let's say, startup costs. Here is an example of the validation we carry out with Comer Industries. As you can see here, we have the digital model built with Particleworks, and on the right, we have the clear casing. Oil distributes very similarly between the digital and the actual prototype. You can see that on top here, there is a lack of oil, so the bearings are in a critical condition in this kind of configuration, given the RPM condition and the oil level. So indeed, in this work, we demonstrated that for several RPM condition and rotational direction, we could predict and match what was observed experimentally in terms of good or bad lubrication levels. So this is the validation. A technician look at the results provided by the clear case and compare the simulation results as well. Of course, this can allow this kind of analysis before implementing a real prototype. So this can take months to build. And if you want to inspect something inside the clear case, it's very difficult, while digital models really can allow for much more in-depth analysis. So it's not only lubrication what we can analyze with Particleworks, but also temperature prediction. So we have different approaches. The first one is a flow-only type of indication that we can achieve with Nusselt correlation. So basically, from the oil physical properties, we can estimate forced convection at the walls and have an information about HTC, the heat transfer coefficient on the wall, Usually with this approach, we then transfer the map to an FEA solver for temperature distribution in the solid. The second step is to actually activate fluid temperature variation inside Particleworks. In this way, we can compute, let's say, thermal equations, so not only force convection due to the velocity of the fluid, but also some thermal equations are enabled. And in this way, we can estimate its fluxes, and we can also check the variation of the temperature inside the fluid phase and implement temperature-dependent fluid properties. So like we could analyze viscosity changing with temperature or other properties of the fluid. Moreover, we can also activate the solid analysis inside Particleworks, so still inside the same interface. The idea is that in this way we have a finite volume method, actually a finite element method for the solid part. So as we will see in the next slide, we can do effectively conjugated transfer and check the coupling, thermal coupling between the fluid and the solid temperature. This usually results in longer simulation, but in a very detailed analysis. Here is an example of a conjugated transfer simulation. In red, we have power, let's say losses, thermal losses due to shear that were estimated by our customer. So from other software or from standard values, we can apply localized losses. And as you can see here on the right, we can then simulate not only the fluid, but also the temperature. So this one is the temperature of the oil phase. As you can see, there is a clear variation between different areas. There is some oil trapped in the bearings area that heats up. There are some more hot areas at the bottom again. And here we have also the solid part in which we can clearly see the areas where losses are greater due to, let's say, the bearings interaction with the walls and the power losses that we applied and as shown in the previous slide. On the right, we can also map the temperature distribution on the housing. And it was interesting here because we could model still in Particleworks a water serpentine integrated in the housing. As you can see, also water heats up due to the interaction with the housing. It's injected at 60 degrees, but it goes up to approximately 90. And we can clearly see the effect of the cooling serpentine at the bottom, resulting also in oil temperature that are lower, and in general also solid and housing temperatures that are lower. So really a very interesting example of coupling solid and multi-phase type of analysis in just one digital model with a transient development of all these aspects. Here is another example of conjugated transfer, really an important feature of Particleworks. We see an e-axle type of configuration. We have gears, but also a knee motor cooled by jets in this case. And we can see the temperature variation in the coil, in the gears, due to the, of course, cooling effect of oil. Okay, so we see in red the most cooled. So the colors are maybe a little bit misleading, but we can clearly see the transient evolution and then reaching a certain plateau of the temperature, both in the e-motor and on the gears. So very comprehensive type of analysis that could allow us to study, for instance, on the e-motor side and on the jets, the influence of flow rate or viscosity of oil on the HTC. So we can clearly see that increasing flow rate on the jet side results in a better cooling on the windings. And also the viscosity of oil can have impact, and we can see that actually it's lower, the HTC, when we increase the viscosity of oil. The same can be visualized in the average temperature of the coils for the different configuration I showed you. Increasing the flow rate will result in lower average temperature on the coil side, while increasing the viscosity of oil will also increase the coil temperature. Air can be simulated in different way in Particleworks, as Particleworks integrates a finite volume solver consisting of this Cartesian grid that is created automatically by the software inside the same simulation. And this allows us for a coupled simulation between the fluid MPS phase and the air finite volume algorithm. We see here an example of an emptying of a bottle. In one case, we have a rotating bottle, in the other one, a static bottle. And we can clearly see the coupling between the air component and the fluid component, resulting in a much faster emptying process for the rotating one due to the inner vortex creation that is seen in this snapshot. Of course, we can apply this also in gearboxes to account for different type of drag due to oil and due to air interaction. On the left, we have the oil distribution when we activate the coupling between the fluid phase and the air phase. On the right here, we see only the air phase, okay, that is present where oil is not, usually, of course. And we can see some splashing inside the air phase. And in general, we can also have a look at the velocity profile for the air phase together with the oil. Here is a comparison, just an example. I don't want to suggest that it's always like this, different, the inclusion or the exclusion of air, but we can clearly see that splashing can be better captured when we also integrate, of course, the drag effect of air. This usually is suggested when the velocities are, let's say, significant, and it's an additional, let's say, numerical aspect that could be integrated when some experimental results wants to be matched, better matched. Air was simulated with a finite volume method in the previous example. In this one, we can have a different type of air simulation. In this case, we focus on the bubble generation inside the fluid phase. This could be due to some interaction between the fluid and the solids, or due to some breakage of the fluid surface. So with this method, we actually take advantage of the coupling between Particleworks and Granulworks, DEM solvers, so we will also see it for powders. So the idea is that the solver will understand when some aeration will occur in the fluid phase and will generate and will also track the development of this multi resolution particle for the bubble size. Okay, so we can see that bubbles here form due to the breakage of the fluid in that section, and they also have a growing law due to the interaction between them. And in this case, it was interesting because we could monitor if air was reaching a critical area that is a pump area. But again, in this case, we are not explicitly simulating air outside here. It's just that the solver will understand when aeration will take place. Here is another example in a gearbox type of application. And we can see that due to the breakage of the fluid and the, let's say, rotations there, we have bubble generated mainly in the area there at the bottom, or due to the interaction with the walls. Sorry, the PowerPoint crashed. So I was saying that that is the second approach. Another feature, another interesting feature that is integrated in Particleworks is the possibility to automate every aspect of the simulation with Python. We have a specifically developed module, Python module called PVPy. It was developed by the software house that is behind Particleworks. So in this way, we can easily modify the project. We can easily create actually from zero a Particleworks project, and we can run pre and post processing in a very automatic way. We can also do screening of some parameters, numerical or material parameters, in a very effective way. For example, here we demonstrated the possibility to automate different type of boundary conditions on the rotational speeds of the input shaft. So really, from this script that we built, we were able, without even opening the interface of Particleworks, we were able to generate what you see on the right, setting the transparency, the colors, and the numerical settings. We set them also dynamically changing the RPM conditions using this, let's say, dictionary and set of different simulations. So it's a very nice way to automate some aspects of the simulation once, let's say, the basic simulation is, we are confident with the basic simulation and the results, okay? So interesting stuff also there. Before showing you a little bit of a demo, I want to also mention some events or references available on the software. So the demo we will have a look in a second, but I want you to invite you at this event. As I mentioned, we will have more contributions on topics like transmission, e-motors, but also traditional engines. This is an event on site that is in Bergamo. You can register by going to our website, Particleworks Europe, and it's at the beginning of June. let us know if you are able to join us on site. Otherwise, we can also maybe arrange something online, depending on your need. So it's going to be very interesting. We have different contributions from important automotive and not only automotive customers, discussing really the most advanced simulation with Particleworks. Regarding already available material, I want to mention that we have many examples, and you can check them out also on the website Particleworks Europe. Here is a little bit of a list. Okay. So regarding the next events, as I mentioned, if you go to the website Particleworks Europe, you have the conference detail, but also the next tech day. So it's an introduction on the methodology if you want to learn more. Basically, it's a full day training. It's gonna happen next week, and you will have access to Particleworks, and you will, let's say, build your first Particleworks model. This is an available demo that you can also check on YouTube if you check Particleworks from 0 to hero. And it shows how in basically 15 minutes we can create a project from scratch. So from creating a new project to setting up the simulation. So this is the simulation domain in Particleworks. You can, let's say, import the geometry very easily. And so those were the STL imported in Particleworks. And then by setting up a filling plane, we can, let's say, initialize below a certain level the fluid domain. Okay. And then there are some physical properties definition. So I won't show you all the details, but you can easily check the steps and the video. Yeah, you will see how fast it is also to apply rotations to the elements with keyframes here. So really fast setup. And then we of course have the numerical settings with a certain particle size and so on. So you can see that again in 15 minutes we were able to generate the first simulation and achieve indication of the lubrication. And in the same YouTube channel, you will also see some post-processing, just to give you an idea of the capabilities and how it's the Particleworks interface, how it looks like. But again, if you want to hear more, my suggestion is really to go to this website, Particleworks Europe events, and check the next tech day. So I would like you to ask some questions if you have. I think this is the best moment to do so.